Dear students, in this video on ray optics, we will study thin lenses in contact and numerical problems based on thin lenses. So let us begin with the combinations of thin lenses. So here, if we have a convex lens L1 and you see, and a point object is placed at its principal axis, then its real image is formed at I1. And if another lens L2 is placed in contact with L1, you see that this ray is coming along this direction, and convex lens is always a converging lens. Converging lens means bringing the rays closer. So this will bring the rays closer to the principal axis and image should be formed here. So see what happens. Now the rays are converging and the final image is formed at this point I, right? So the first lens L1, this is object and this is image. For the second lens L2, this is object and this is image, and this is a real image. So we are going to follow this idea only. So here, when rays from object O pass through lens L1, its real image is formed at I1. Now using the lens formula for this L1, what do we get? You see, focal length of this L1 is f1. So 1 upon f1 is equal to 1 upon v1. See, the image distance for this I1 is v1. So for the first lens, the object distance is u, image distance is v1. So 1 upon f1 is equal to 1 upon v1 minus 1 upon u. And for second refraction from L1, this L2, this I1 is object and the I is image. So here the image I1 will act as an object for refraction through lens L2. So the final image is formed at I, and now the lens formula. So here 1 upon f2 for second lens is equal to 1 upon v. The v is the image distance minus 1 upon u. Now here u is equal to v1, the object distance. And now adding these two equations, you can see that this 1 upon v1 minus 1 upon v1 here and plus 1 upon v1 from the previous equation, they will be cancelling out, and on the left side we get 1 upon f1 plus 1 upon f2, and on the right side we get 1 upon v minus 1 upon u. And you see, now for the combination of these two lenses, you see these two lenses were in combination. If this whole combination is replaced by a single lens, then the object distance was u and the final image distance is v. So the focus of this combination is, say, f. So this focal length or equivalent focal length of the combination will be given by 1 upon f. See, 1 upon v minus 1 upon u will be equal to 1 upon f. So this is going to be 1 upon f. So that means 1 upon f is equal to 1 upon f1 plus 1 upon f2. So f is a equivalent focal length. And see, 1 upon f is power. So power of combination is p. 1 upon f1 is power of lens 1. 1 upon f2 is power of lens 2. So powers are added up. You can see that when lenses, and see, we use these powers along with their sign. So if the lens is a convex lens, power is positive. If a lens is a concave lens, power is negative. So we use the formula along with the signs. And now let us take problems. Two lenses of focal length 10 cm and minus 20 cm are placed in contact. Find the focal length, power and nature of the combination. So you can see that this one is positive. Positive means it's a convex lens. This one is negative, means it is a concave lens. So here, using the formula, 1 upon f is equal to 1 upon f1 plus 1 upon f2, or 1 upon f is equal to 1 upon 10 centimeter plus 1 upon minus 20 centimeter, and you simplify it, you get minus 1 upon 20. Take the reciprocal. The combined focal length comes out to be minus 20 centimeter. And the power of combination is, if you take focal length in centimeter, then it is 100 upon f. So 100 upon minus 20. So the power of the lens is combination is minus 5 diopter. And since the power is negative, the combination is diverging combination. That means the combination will act as a concave lens. And another one. An object of size 2 cm is placed at 40 cm from a Plano convex lens with radius of curvature 15 cm and mu. Refractive index of the lens is 1.5. Find the position, size and nature of image and find the magnification by the lens. So first thing first, the focal length of the lens is not given. So we will find out the focal length using this lens maker's formula. And you are familiar with this formula. 1 upon f is equal to n2 upon n1 minus 1 into 1 upon r1 minus 1 upon r2. Now here, let's look at it. N1 is the rarer refractive index of the rarer medium, and here it is air. So N1 is equal to 1, and N2 is refractive index of the second medium, that is the refractive index of the lens, and it is given to be 1.5, and R1 is refractive index of the first surface. So see, a Plano convex lens is, this side is convex and this side is plane. So see, I'll draw it once again. This side is convex and this side is plane, and the rays are coming from here, you can see. So the radius of curvature of the first surface is along this direction, so R1 is positive, and radius of curvature of a plane surface is infinite. So all these values we can put in this lens maker's formula. Okay, so now we get N2 is equal to 1.5, N1 is equal to 1 air, R1 is plus 15 centimeter, and R2 is infinite. So put all the values. 1 upon f is 1.5 from here, minus 1 into 1 upon R1, that is 1 upon 15, minus 1 upon R2, that is 1 upon infinity, and 1 upon infinity is 0. So from this difference we get 0.5, and from the bracket we get 1 upon 15, and simplify it, you get 1 upon 30. And now take the reciprocal, you get focal length as 30 centimeter. So the Plano convex lens is a convex lens of focal length 30 centimeter. And now we can use the lens formula, thin lens formula. So, according to the question, the object is placed at 40 centimeter. That means object distance is minus 40 centimeter and size of the object is 2 centimeter plus 2 centimeter because it is above the principal axis. So, if the lens is like this, the object is placed above the principal axis. So, size of object is positive and object is placed on the left side and the incident ray is towards the right side. So, object distance is negative. And now, using this lens formula, 1 upon f is equal to 1 upon v minus 1 upon u, we have to find out v. So, keep 1 upon v on left side on one side and take this minus 1 upon u to the other side, it becomes positive. So, what you get now is 1 upon v is equal to 1 upon f plus 1 upon u and put the values, that is equal to 1 upon 30 plus 1 upon minus 40 and take LCM and simplify, you get 1 upon 120 and take reciprocal. You see, now 1 upon v is equal to 1 upon 120, take the reciprocal and now you get the position of image plus 120 centimeter. That means image is formed on the other side, right side of the lens. That means if my lens is like this and object is placed here, then its image is formed somewhere here. It was 40 centimeter here and it is formed at 120 centimeter on the right side along the direction of the incident ray because V is positive. And now let us look at the magnification. Now magnification M is height of image upon height of object and it is also equal to V upon U. So put the values. The value of V is plus 120, value of U is minus 40 and this is equal to minus 3. So magnification is minus 3 negative, and since magnification is negative, that means the image is real. And from this relation only, the size of image will be equal to the size of object, take it to the right side into minus 3. So size of image is equal to minus 3 into size of object, minus 3 into 2. Size of object is plus 2, so that is minus 6 centimeter. Now since it is negative, that means the object is inverted and magnification is also negative. Magnification is negative, object is real, image is real and size of object is negative, that means object is inverted. So nature of the image is, it is real and inverted. Let us look at the next problem. A very good problem, board problem. Even the previous problem was a board problem only. So let us try to understand the question first here. You are given 3 lenses L1, L2 and L3. See, L1, L2, L3. Each of focal length 20 centimeter. So focal length of each lens is 20 centimeter. An object is kept at 40 centimeter in front of lens L1. This object is placed at 40 centimeter in front of L1 as shown in figure. The final real image is formed at the focus I of lens L3. So the final image is formed here and it is at the focus of lens L3. Its focal length is 20 centimeter. So final image is formed at 20 centimeter. Find the separations between the lenses L1, L2 and L3. So we have to find out separation between L1 and L2, which is x1, and separation between L2 and L3, which is x2. So we have to find out these values one by one. So let's see how we do it. Okay. So first thing first, for lens L1, we know the position of the object and focal length of the lens. We can find out the position of the image. So using the lens formula, for lens L1, focal length is 20 centimeter, object distance is minus 40 centimeter, and the lens formula is 1 upon f is equal to 1 upon v minus u, 1 upon v minus 1 upon u, and then 1 upon v will be equal to 1 upon f plus 1 upon u. Take it to the other side and put the values of f and u. You get 1 upon 20 plus 1 upon minus 40. Simplify, you get 1 upon 40, or v is equal to plus 40 centimeter. Take the reciprocal. So that means position of image. The image made by this one will be at 40 centimeter from here, from this one at 40 centimeter. Okay. Now, there is a very important information here, that the final image is formed at the focus of L3. Final image is formed at the focus of L3. See, this is at the focus of L3. Focus. Now, if you remember the definition of this focus, then image is formed at focus only and only when the incident rays on the lens are parallel rays. That means the rays falling on L3 must be parallel. Okay. So, as the final image is formed at the focus of lens L3, the incident rays on it must be parallel to the principal axis. So, the rays emerging from L2 must be parallel. Okay, that's very clear, that the rays incident on it should be parallel, so that after refraction they reach at the focus. So, the rays emerging from L2 should be parallel, and rays coming on L3 should be parallel, and after leaving L3 they reach at the focus. Okay. See. Okay. Now, this can happen only and only when, another definition of this focus only. Now, if the rays are starting from focus and they fall on a lens, then after refraction they become parallel. So, this must be focus of the lens L2. The rays must be coming from the focus of L2, and then L2 makes them parallel like this. That means this point should lie at 20 centimeter, because focal length of each one is 20, and the image formed by L1 should be at this focus only. So, the outcome is very clear. This is the position of image. It is at 20 centimeter, and image distance for the first lens is 40 centimeter. So, it should be at 40 centimeter, you see. So, the image formed by this one is at point I at 40 centimeter, and this image is object for lens L2, and since it is at its focus, it makes it parallel, and it falls on L3 as parallel rays, and L3 makes a real image at its focus. So, situations are clear, and now the separation between this L1 and L2 is clear. 40 plus 20, that is 60 centimeter. And for L2 and L3, if you look at this L2 and L3, see, For L2 and L3, since these rays are parallel, the distance can be anything. It can have any value. So, we cannot tell exact value of x2. So, see. So, separation between lenses L1 and L2 is 40 plus 20, 60 centimeter. And separation between L2 and L3 can have any value because the rays are parallel. A very good question. Another board problem and a very good question. A beam of light converges to a point P. A lens is placed in the path of the convergent beam 12 centimeter from P. At what point does the beam converge if the lens is a convex lens of focal length 20 centimeter and a concave lens of focal length 16 centimeter? First, let us try to understand the question only. See. A beam of light converges to a point P. So, it is like light rays are coming and they are converging at point P. And now what they are saying is, a lens is placed in the path of the convergent beam at 12 centimeter from it. So, this is the path of the rays, and from here a lens is placed here at 12 centimeter. Right. Now, you have to find out at what point does the beam converge. That means you have to find out the position of the image. See, initially the rays were coming along this direction, and now a lens is placed in the path of the incoming light, incident light, and you have to tell the position of image. The distance of this point P is 12 centimeter from the lens. So, this point P will act as object for this lens. Remember, the light rays are falling on lens like this and they are meeting at point P. So, this point P will act as object for the lens, and then final image will be formed by the lens. So, let's see how it works. Point P will act as object for the lens. So, object distance is positive plus 12 centimeter. See, object distance doesn't always have to be negative. Object distance can be positive, as in this case. And in the first case, it is a convex lens. So, the incident rays are these two, and they were meeting at point P, and at 12 centimeter from point P, this lens is placed. So, now they will not meet at this point P, and you know that convex lens is converging. So, the rays will meet closer to the lens, converging lens. So, we expect the image to be formed somewhere nearer the lens. And since the direction of incident is this ray is this one, and the object distance is also along the same direction, so this object distance is positive. And now, using the lens formula, f is plus 20. See, the focal length part A, convex lens of focal length 20 centimeter. So, focal length of convex lens is given as plus 20 centimeter, and the object distance is plus 20 centimeter. So, using the lens formula, 1 is equal to 1 upon v minus 1 upon u, and I want to find out object image distance. So, keep this 1 upon v on left hand side and take to the other side. You get 1 upon f plus 1 upon u. Put the value of f and u, both are positive. Take LCM and simplify. You get 8 upon 60. Take the reciprocal. You get V is equal to plus 15 upon 2 centimeter or 7.5 centimeter. So V is 7.5 centimeter. So if you look at this diagram now here, the rays will converge at this point at 7.5 centimeter from the lens. So object is at 12 centimeter and image is at 7.5 centimeter. You must understand the working of the lens. And now for the second part, a concave lens of focal length centimeter. Now in place of convex lens, I have placed a concave lens at the same distance. So look at this diagram now. Now the rays are coming like this and they were converging at point P. So point P is object and object distance is along the direction of incident ray. So object distance is positive. Now the nature of a concave lens is diverging. So the rays were coming along this direction. So this lens will diverge them. The rays will be diverged and they will meet somewhere farther. They will meet beyond this point P, somewhere here. That is our expectation. So let us see what we get by calculation. So here the focal length is minus 16 centimeter and using the same lens formula, put the value of F and U, you get 1 upon 48 and V is equal to plus 48 centimeter. That means the image by this concave lens will be formed at farther distance of 48 centimeter. Real image will be formed and see this is a concave lens, but still the image formed will be a real image only and at 48 centimeter. So with this I come to the end of this unit, this thin lenses, and I hope this is beneficial to all of you. Thank you for watching it.